All right, good morning, guys. Sorry, I'm running a few minutes behind. I woke up to my apartment at like 80 degrees today because our AC handler broke overnight. So I'm trying to get that wrangled too. Got the doc cam fired up. We'll get started here in just a second. Okay, yeah. So hopefully everybody is feeling pretty comfortable with limits. Hopefully we've practiced and worked on the homework sufficiently that we're not afraid of any real limits. We can handle all of them. What do you mean camera's not connected? Yes, it is. What? Well, I guess we can try that. Right. So this week is a big week for us because it's going to be the first time we start talking about the principal object in Calc 1, which is the derivative. So, oh boy, that lower resolution really is a hit. I might actually, let's see if this will work. Yeah, that's a little better. There's a bunch of different ways to try and motivate the concept of a derivative. There's a bunch of different ways to try and talk about the thing that we're going to talk about. One that I like a lot is this idea of linear approximation. So if you have a function like this, any function, nice smooth graph, smooth curvy graph, there are a handful of things that we'd want to do with it. You know, you've seen in your pre-calculus classes, we might want to find where the function is increasing, where the function is decreasing, where the function is increasing. You might want to find this max or this min and try and identify it as a local max or a global max. You know, if it had some x-intercepts, we'd want to find those in an algebra class. One of the other things that we like to do as people who study functions is to try and recognize how fast the function is changing. And I know you've seen this concept of an average rate of change before. Definitely seen them in various algebra classes. It turns out that the things I talked about at first, increasing, decreasing mins and maxes, are really closely related to the concept of a rate of change. If you imagine this as a ski slope, and you're a little guy along it trying to ski, at any given point along this graph, your skis are pointing in a certain direction, right? Like there, imagine my pen are your skis. The skis are flat, they're straight lines. But the graph is curvy. It's definitely not flat. In fact, as it's drawn here, it doesn't appear to be flat anywhere, right? It appears to always be curving, which means that there is no single rate of change for the function. You may remember in college algebra, we characterize linear functions as functions whose rate of change is always constant. The rate of change, or slope, for this guy is definitely not always constant. The slope over here appears to be kind of like this. The slope at the top here kind of looks like that. The slope on this little down segment here is like this, because my skis would be pointing down if I was skiing along it. Down here, it appears to be flat again, maybe. And then it's pointed up like this. The question we would like to get at is if you pick a point, like that little dash mark down there on the x-axis, and I ask, what direction are your skis pointed right at that x value? So if you look at this x value, you come up to the graph, can you find the slope of the function right there? A slope isn't really the right word to use because this function isn't a line, so its slope is definitely not constant. There's no real notion of slope that we can tie directly to this function. But I can ask myself, if I were skiing along this hill, what direction would my skis be pointed at that moment? Right? Am I going uphill or downhill? And if I'm going uphill, how fast am I going uphill? If I'm going downhill, how fast am I going downhill? So in other words, yeah, can we find the slope of the line that this pen appears to be sitting on top of? Definitely over here, I could say that that slope would be positive. Here it appears to be negative and like kind of shallow, maybe -1/2. Here it appears to be negative and a little bit bigger, like maybe -1 or -2. It turns out that the main operation in calculus gives us an answer to that question. It will give us another function. Instead of calling it f, we call it f prime, or the derivative of f. And that function, instead of returning the height along this graph, returns the slope. And the tools we need to get that function are exactly the things we've been playing with over the first few weeks of the semester: difference quotients and limits. So I'm going to label this guy right here as A. And this point up here then, because it's along the graph of f of x, and the x value is A, has to be A comma f of A. Right? The y value along the graph of the function is always f of that x value. If I look a little bit to the right, say I walk h units to the right over here to a plus h, then I can locate the point on the graph of the function f above that. This will be a plus h, comma, f of a plus h. I want to make sure everybody really understands why these y values at these points are what they are. It's not uncommon for this to be a sticking point, so I really do want to make sure we're comfy with that. Are there any questions why those points have the labels they do? Okay, so any point on the graph of f of x is something comma f of that very same thing. Since this x value is a, that's a comma f of a. I want to look a little bit apart from him, so call this a plus h. Then this has to be a plus h comma f of a plus h. Why am I choosing a and a plus h? So that things line up with the notation that you've seen for difference quotients before. So I'm looking ahead at what's to come, thinking about what you've seen in the past. Now, I'm going to draw in a little line connecting those 2 points. This line has a name. It's called the secant line. I'm going to make it a little bolder. Secant line is the name for the line connecting any 2 points on the graph of a function. We call it the secant line. The slope of that secant line is the average rate of change for the function f from x equals a to x equals a plus h. And what is that slope? Well, we take the rise over the run. So I'll take the difference of y values and divide it by the difference of x values. That's f of a plus h minus f of a divided by a plus h minus a. But that denominator can be simplified. This is the same as f of a plus h minus f of a just divided by h, right? The a plus h minus a, the two a's there go away. They cancel. So this is the thing you've seen called the difference quotient, and it gives you an average rate of change for your function. But let's return to the skiing analogy. If you're skiing along this hill, your skis do not poke down through the hill. This doesn't tell you exactly how you're pointed at any given moment. What I want to know is not what's the average rate of change from here to here. I want to drag this point up here to be the same as that point and get the instantaneous rate of change. So the thing that we're going to discover here, the derivative, the thing I call f prime, is what you get as you drag this point closer and closer and closer and closer along the graph to this point. In other words, I want to see what happens if I hold this fixed and I send h to 0, which brings this guy over to this guy. That will give me what's called the slope of the tangent line. The tangent line looks like this. It's the line that just barely kisses the graph there, and it does so with exactly the right slope. So this guy right here, he's the tangent line. And it's the same notion of tangent that you met in trigonometry. There's a geometric definition of the tangent function that comes from looking at where a line that is tangent to the unit circle intersects the x-axis. And that tangency is the same sort of tangency we're seeing here. So what I'm after, the instantaneous rate of change for this function, the slope of the function at a point, is also called the slope of the tangent line. And the way we get that is by sending h to 0 in this formula down here for the slope of the secant line. If the y-axis here, so step outside for a second. I want to just give you a little bit of concept stuff before we dive in. If my function here was measuring distance, like how far has a car gone from where it set off, and my horizontal axis here was measuring time, then the slope of the secant line would be like the average speed between those two times. The slope of the tangent line would be what's reading on the car's speedometer at any moment. It's the instantaneous rate of change. It's the speed at that second. So the value of this derivative thing is that it tells us how fast that function is changing, not over some average, not over some interval on average, but exactly how fast that function is changing at this moment. So think about average speed in a car, how long you spent driving versus how far you went versus how long you spent driving, versus your instantaneous speed, what your speedometer says at every moment along the way. If I leave here to drive up to the store and come back, then I start off at a standstill, and then I do some accelerating, and maybe I slow down a little bit, and I accelerate a little bit more, and then eventually I stop. If the whole trip takes me like 5 minutes and I go 1 mile, then my average speed would be 1 mile divided by 5 minutes. But my actual speed over that trip varies quite a bit, right? Like I started off at a standstill. I wasn't always going that same average speed. So it's worthwhile to try and get this very specific information out. And for a lot of real world applications, it's super duper important. So just a few analogies to try and help you understand what we mean by instantaneous rate of change before I give you the definition. The derivative of f of x at x equals a is f primed of a. That's the notation. And it's defined to be the limit as h goes to 0 of this difference quotient. And I would also say that f primed of a is the instantaneous rate of change for f of x at x equals a. And then even one more here, f primed of a is these all mean the same thing, but you'll hear different verbiage, is the slope of the tangent line to f of x at x equals a. So these are this is the main object of study in Calc 1, the derivative. And it has these different interpretations. On the one hand, it's just got this name. It's called the derivative. On another hand, you can think of it as the instantaneous rate of change for that function at that point. And lastly, if you want to, the instantaneous rate of change for that function at that point is the slope of this tangent line. So a few nice, easy problems to kind of get us used to these ideas and get us a little practice computing this thing involves finding equations of tangent lines. So that's where I would like to begin, or at least just finding slopes of tangent lines. I'll make sure I'm not leaving out any important definitions. Oh, okay. There is one other way to formulate this. But I think to keep things simple, it's best if we don't do that. Yeah, let's keep this simple. All right. So, this is all section 2.8, by the way. So chapter 2 ends with these definitions, And then chapter 3 begins with some sneaky techniques to compute this thing. So let's go ahead and see if we can do a few of these computations for a few specific functions. Let's take the function 3 over x and try to find the equation of the tangent line at the point 3, 1. Okay. So a here is this number. It's the place where we're trying to find the tangent line. And f is this function. And to find the equation of a tangent line, just like to find the equation of any line, I need two things. I need a point, and I need the slope. Let's find the slope of the tangent line. The usual notation for that is m tan, and it's f primed of a, which is 3. And according to the definition we just wrote down, this is the limit as h goes to 0 of f of a plus h, that's f of 3 plus h, minus f of a, that's f of 3, all over h. So I need to compute this limit. And the only way to do this is to plug these things in, try to clean up and simplify. Working with this difference quotient object is something that hopefully you have a meaningful amount of practice with. We've done some of it in this class, and ideally you've done some of it in your pre-calculus class. F of 3 plus h is what you get by plugging in 3 plus h for x in the formula for f of x. So that's 3 over 3 plus h. F of 3 is what you get by plugging in 3 for x. So that's minus 3 over 3. And then all of this is being divided by h, and I recommend some parens. Remember, fractions are grouping symbols. Now, to clean this up, I need to have a common denominator up there in my numerator. So this is the limit as h goes to 0. 3 over 3 is the same as 1. Let's start there. So this is 3 over 3 plus h minus 1 all over h. And then in order to have a common denominator up here, I need to write this guy as something with the same denominator as this. So I'll multiply the 1 by 3 plus h over 3 plus h. So this is 3 over 3 plus h minus 3 plus h over 3 plus h, all divided by h. Now that the two fractions upstairs have the same denominator, I can write them as a single fraction. So this is the limit as h goes to 0 of 3 minus parentheses 3 plus h all over 3 plus h, all divided by h. And if you do this subtraction upstairs here, three minus 3 plus h is negative h, right? That's 3 minus 3 minus h. You have to distribute this negative. So the 3's go away, and the h which survives there is negative. And this is what we're left with. Now remember the way to handle this sort of thing. If you've got one fraction divided by another fraction, you flip and multiply the bottom. So this is negative h over 3 plus h times 1 over h. And now these h's can cancel. And you have the limit as h goes to 0 of negative 1 over 3 plus h. And this is a limit we know how to take, right? This is not a difficult limit. Here I can just plug in 0 for h, and I'll get negative 1/3. Now that's a lot of work, but it's work worth doing, and I really would like you to be careful with your notation like I am being here, right? So I always write the limit. I never skip writing the limit. Be very careful with your algebra. It's so goddamn important that you're careful with your algebra in this class. If there's one thing that'll bite you in the butt, it's sloppy algebra. And just keep everything nice and organized. What is this thing that we just found? It's f primed of 3. It's the slope of the tangent line. Keeping your work organized will allow you to stay strategic. It'll allow you to keep in mind what it is you're trying to do. So what else should I do? I want the equation of the tangent line. I now have the slope of the tangent line. What else do I need? If I want to write down the equation of a line, any line, I need the slope and what else?
Is that y equals mx plus b?
If I knew the y-intercept, I could use y equals mx plus b. But I, in general, can get away with any other point. So remember the point slope form of a line? If you happen to have forgotten this from your algebra class, it's forgivable, but you absolutely need it now. There's no escaping it. This is why your algebra teachers kept being like, no, stop using y equals mx plus b. Start using this, because we use it all the time in Calc 1. So this is the equation of the line with slope m passing through the point x1 comma y1. So the slope and any point, that's what I need. Not necessarily the y-intercept, but any point on the line. A point which I know has to be on this line because it is a tangent line to that function is the point on the graph of that function where the x value is equal to 3. Hammy, bud. Hammy! Hold on. It's okay, I love you. If you're gonna do that, just go somewhere else, all right? You're a good boy. Sorry. So what do we use for our point? The point of tangency. A comma f of a, which here is 3 comma f of 3. Oh. Because I'm looking for the equation of the tangent line at x equals 3. And just like on our picture over here, one point which is guaranteed to be on the tangent line is the point where the line is tangent to the graph, and that's always a comma f of a. So here the point is 3 comma f of 3. What is f of 3? It's 1. If I plug in 3 for x here, 3 over 3 is 1. So my point of tangency, the point I will use in my point slope formula, is 3 comma 1. Are you guys with me on this? Do you see why that's the case? The line I'm trying to find the equation of is a tangent line. Tangent line touches the graph of the function at the point of tangency. So I know that the point of tangency is on the tangent line, which means I can use that point as my point for point slope. So finally, the equation of the tangent line to f of x equals 3 over x at x equals 3 is y minus y1, well, y1 here is 1, equals m, my slope. My slope is negative 1/3 times x minus x1, that's x minus 3. So that's it, that's the equation of the tangent line. You can put that into y equals mx plus b if you want to. You don't have to, but since my next step is going to be to draw this thing for you, I will go ahead and put it in there. So that's negative 1/3 x plus 1. So y equals negative 1/3 x. When I distribute this 1/3, I'll get a plus 1 there, and then another plus 1 from this, so that's plus 2. So let me hold on to that. I'm going to move the page up a little bit and draw for us the graph of this function with the tangent line.
Mr. P, I forgot the last few things.
What can I help with here? So we did that limit calculation. That gives us f primed of 3, which is the slope of the tangent line. And that was all of this. And then once we had the slope, we said, okay, well now I'm going to use the point slope form of a line. That's this equation right here. We need to burn this into our brains if it's not already burned in. Then to use this, I need some point that I know is on the line. And the point that I know will be on that line is the point of tangency, a comma f of a, which is 3 comma f of 3. Because here a is 3. We're trying to find the equation of the tangent line when x is equal to 3. So that point, 3 comma f of 3, is 3 comma 1, because f of 3 is 1. And then I just take this point for my x1, y1, and this slope, and I plug into this formula. And that gives me this equation. All right, I'll leave this here for just a second. You guys can copy anything down that hasn't been copied down yet. Remember, in your notes, you should be writing everything that I write on the .cam.
Thank you.
Of course. This might be an okay time to pause. Are there any other questions at this point?
So can you explain again how you got 3, 1 for the point?
So if we look back here, one point that I know is on the tangent line, one point that I know is on this line, is the point where it kisses the curve to which it is tangent. Right? The tangent line is the line that just kind of comes along here and barely kisses the graph of my function right at that point. So this point is a shared point. It's on the graph of f, and it's also on the tangent line. That point is a comma f of a. It's the point on the graph where I'm trying to find the tangent line. Since on this example, they told us to find the equation of the tangent line to that function when x is equal to 3, my point of tangency is 3 comma f of 3, right? A comma f of a. And f of 3 is 3 over 3, which is 1. So that point is 3 comma 1.
Okay, I understand now. Thank you.
Cool. All right. So I will do my best here to sketch a graph of this function for you guys. 3 over x looks a lot like 1 over x. It's just been scaled up by a factor of 3. So he kind of looks like this. And right here is the point 1 comma 3. But the point I'm looking at is over here at 3 comma 1. So this is 3 comma 1. And my tangent line is y equals negative 1/3 x plus 2. So he's got a y-intercept right here. And he goes through this guy. So my tangent line looks like this. Okay. Right. And this graph, the whole graph, the big graph here is f of x equals 3 over x, of course. Okay. So the tangent line is the line that just barely kisses the graph of the function. It's like in the same way that a line that's perpendicular to the radius of a circle is tangent to that circle, this line is perpendicular to that graph at that point, perpendicular to the kind of radius of curvature. The big thing for us is that it represents an instantaneous rate of change. Because the tangent line here has a negative slope, this function must be decreasing. So you may remember in your pre-calculus classes, when you talk about increasing and decreasing, you always use open intervals because it's very hard to say whether a function is increasing or decreasing at a point. Now you can answer that question. Because the tangent line has a negative slope at this point, I can say for sure that this function is decreasing at this point. So that idea of instantaneous rate of change or instantaneous velocity is going to allow us to expand the sort of things that we were doing in previous algebra classes. questions that we could answer over an interval but not at a point, we can now answer at a point. The important thing for right now is that you guys are comfortable with how we came up with this equation for the tangent line and how we knew what this picture would look like. So those are the things I would like to focus on right now. First, any questions about this procedure that led to us finding the equation of the tangent line? All feeling good? Yeah, go ahead, please.
Okay, so I get the 1 point where 3, comma 1 is, but what's the point that we use on the y value? Is that 2, and where do we get that from? Oh, okay, never mind. Oh my God, sorry.
That's all right, yeah. So when I put my tangent line into y equals mx plus b, that told me that my y-intercept for the tangent line was 2. That's all.
All right, thank you.
How do we get the slope again?
The slope is this big limit calculation.
There you go. Thank you. Yeah, that's what I was looking for.
Okay, yeah, I'll leave that here for a second to patch up any gaps in the notes. So the slope is the big thing, right? The slope is the hard thing to get. And that's coming from this derivative, f primed of 3, which, according to the previous page, is this limit. And then this limit was all this work to calculate.
So in the slope equation, you don't plug in 3 for x to find the y-intercept?
Which equation are you referring to?
Y equals mx plus b.
So I plugged in, no, so the equation of the tangent line down here should have both a y and an x variable in it. So I plug in for m, I plug that, my slope in here, and then I plug in for x1 and y1, my point. So x1 and y1 came from this point 3, 1, and my slope m came from this big limit calculation. So for m, I plug in -1.
Right, but how did you find,
I'm sorry, say that again?
right, but how did you find the y-intercept? You're saying the y-intercept is 2?
So I started with the point slope form of the equation right here. See, I plug in 1/3 for m, 3 for x1, and 1 for y1. And then I just simplified this, right? I just distributed the -1/3 and I added the 1 back over. So like I give you an equation of a line in one form and then ask you to put it in slope-intercept form. That's all I did there.
Right, but how did you get that the y-intercept is 2?
So this is the same as y minus 1 equals -1/3 x plus 1. And then I added this 1 over here.
Right, but in the graph, it's crossing 2. How did you know that it's crossing 2? It's the same question that other chick asked, but she was like, "Oh, I got it," and I didn't get it.
Where this equation comes from?
No, I know where that equation comes from. How do you know that that tangent line crosses through the 2 at the y?
Because this is the equation of the tangent line, and it has y-intercept too there, right? This is mx plus b.
So b is the y-intercept?
Yeah.
Oh.
Yeah, think back to like college algebra, right? Y equals mx plus b has slope m and y-intercept b. So this line right here has slope 1/3 and y-intercept 2.
Oh, so you don't need to find it. You don't need to set y.
No. Yeah, because I put this into that form, I'm able to read off the y-intercept.
Okay, thanks for the reminder.
Yeah, no problem. No problem. That's what we're here for. What else are we thinking? Everything else feel mostly good?
Yes, sir.
Okay. So I'd like to do an example from the world of physics, because the world of physics is so nice for this stuff, but I'm not really thrilled with the examples the textbook supplies. So what's the velocity after 5 seconds? Sucks. Maybe. Well, maybe the thing to do here is to give you the general formula for a tangent line. And we'll do one more tangent line calculation. And then we'll talk a little bit about physics. So you can take that point slope equation and the definition of the derivative and combine those to see that the formula for the equation of a tangent line at the point, or at x equals a, so at the point a comma f of a is y minus y1, but y1 will always be f of a, equals m, but m is always f primed of a, times x minus x1, but x1 is a. So here's another formula that I would consider holding on to if I were you. All right, it's the point slope form with the specifics plugged in for a tangent line. Let's find one more equation of a tangent line. Let's do, yeah, let's find the equation of the tangent line. To this quadratic function, f of x equals x squared minus 8x plus 9. At x equals 3 again. So I'm hoping to use this formula, which means I'm going to need a, f of a, and f primed of a. This guy is always a. So my point, here, I'll do it like this. First, I need the point. It's always a comma f of a. Here, a is 3. So that's 3 comma f of 3. And I need to figure out what f of 3 is. F of 3 is what I get when I plug 3 in for x. So that's 3 squared minus 8 times 3 plus 9. So what is that? That's 9 plus 9 is 18 minus 24. That's minus 6. So this point 3 comma f of 3 is 3 comma negative 6. And then the other thing I need is the slope. The slope of the tangent line is always f primed of a. Here a is 3, so that's f primed of 3. And that by definition is the limit as h goes to 0, f of 3 plus h minus f of 3 over h. Just a coincidence that this example has the same a value. Right? It will not always be 3, of course. So now I'm going to work on this limit. That's equal to the limit as h goes to 0. F of 3 plus h is what I get by replacing these x's by 3 plus h in parentheses. So that will be 3 plus h squared minus 8 times 3 plus h plus 9. So that's f of 3 plus h. And then from that, I'm going to subtract f of 3. F of 3 is what I get when I plug 3 in here. Oh, but I've already done that. Actually, that's negative 6. Minus, yeah. And then I divide all of this by h.
Can you pause there for like a
Yes.
whole 60 seconds?
Sure, yeah, take a second. This would have been that may have been.
So that's f prime of a equals the limit as h is 0.
Yep, of f of a plus h minus f of a all over h.
And we use that anytime it says find the equation of the tangent line.
Yep, or anytime you just want the slope of the tangent line, or anytime you want the derivative.
Oh, okay. So it could be for a secant or something.
Well,
Maybe not a secant, but
secant, but there could be another situation where I ask you for just the slope of the tangent line, or I ask you just for the derivative on its own, rather than asking you for the equation of the tangent line as a whole. So I could say, just tell me what is f prime of 5, and then you would use that same formula. I could ask you what's the slope of the tangent line when x is equal to 3, and you would use that same formula.
okay.
So
Thank you.
we've got the limit as h goes to 0. I'll square this out. 3 plus h all squared is 3 squared, plus 2 times 3 times h is 6h plus h squared. And then I'm going to have to subtract from that 8 times 3 and 8 times h, so that's minus 24 minus 8h. And then I've got this plus 9 here. And then minus minus 6 is plus 6. So all this divided by h. We got to be careful making sure that this negative 8 gets distributed to both of these. And then we can combine our like terms. 8h. Yeah, this term right here, this is an 8h because it's coming from this guy distributing. All right, so my constants, if I take all those guys, I've got 9 plus 9 plus 6, right? That's 18 plus 6, that's 24. So I have the limit as h goes to 0 of, let me do this right, minus that, yeah, okay. Oh, yeah, so if I combine this 9, 9, and 6, I get positive 24. With this guy, that's 0, right? Positive 24 plus negative 24, that's 0. So what survives? I've got this 6h, so I'll cross off the guys that cancel to 0. Those things cancel to 0. Everything else that's left, I've got 6h minus 8h, that's minus 2h, and I've got this h squared. So I have h squared minus 2h all over h. And now I can factor an h from the numerator, which is good news because I need that to cancel the h downstairs. So these then cancel. And I have the limit as h approaches 0 of
Excuse me, sir.
yes.
Okay, so on the top, we have 9 plus 9 should be 18. I don't know why they give 0.
9 plus 9 plus 6 is 18 plus 6 is 24. And then this guy
Okay, thank you.
makes 0.
Okay.
I had to think about it for a second too. It's all good. Other questions? Okay, so then we have our point and we have our slope. So we can write down the equation of the tangent line. Y minus f of a is equal to f primed of a times x minus a. Everything here except for the x and y should be numbers. So f of a, what was f of a? Well, I come back here to my point. A was 3. F of 3 is negative 6. This is y minus negative 6 equals f primed of a, f primed of 3, my slope is negative 2. That's what I got from the limit, times x minus a, and a here was 3. So this is the equation of my tangent line. And we could simplify, we could put this into y equals mx plus b, we could do whatever things you want to do with a line. But at this point is when we can declare victory. Right, now we have the equation of the tangent line. Just for fun, this is the same as y plus 6 equals negative 2x plus 6, which is itself the same as subtract 6 from both sides, y equals negative 2x. So simplifying there is worthwhile because it makes things nicer. I'm not going to draw this graph by hand, but I am going to flip over to Desmos here and show you how these two things interact. Before that, any questions on the calculations? I'll zoom out a little bit so we can see kind of everything at once. Questions on this calculation, finding the equation of the tangent line to that function at that point.
At the very last piece, h minus 2 equals -2. How did you get -2?
So the limit as h approaches 0 of h minus 2. So I'm sending h to 0. So if you plug in 0 for h here, you get -2.
Okay, thank you.
Of course. So let me tab over to Desmos. Oh, I already have a Desmos tab here. Get rid of these things. We're not playing with those right now. Zoom out to get the right scale. Okay, now my point of tangency is 3, -6. This point right here. And then my tangent line is y equals -2x. And we see that that tangent line just kisses the graph of this function right here at the perfect slope. So this line has the same slope as this function at that point. And you can actually think of this graph as being made up of infinitely many, very, very little line segments, each having the appropriate slope at each point. And that's really the big idea here. So you may want to sketch this or take a little screenshot or something like that so that you can add it to your notes. It is nice to have the picture. We do have the picture from the previous one, but more examples never hurt. I saw a request in chat to go back to the step here where we're finding the slope. So I'll do that in just a second after you guys have a second to look at and interpret this. Any questions about the picture? Okay, so let's come back to the dot cam then. There was a step in finding the slope that somebody wanted to see a little bit more closely, right? What step was that? So the second step here. So to pass from here to here, I FOILed this out. That's 3 plus h times 3 plus h. So my firsts are 9, my inners and outers add up to 6h, and my lasts are h squared. Here I distribute the -8 to the 3 and the h, so I get -24 minus 8h. This 9 is this 9, and this minus 6 makes plus 6. Right before we start distributing, so from here to here, I just plugged into the formula. So f of 3 plus h is what I get if I take the formula for f of x and everywhere write 3 plus h instead of x. So f of 3 plus h is 3 plus h squared minus 8 times 3 plus h plus 9. So everything that's in this first bracket is f of 3 plus h. This bracket is f of 3. F of 3 is 6 because when I plug 3 in for x in my formula for f of x, I get -6 out. Yes, the 3 plus h comes from the a plus h. Here a is 3, so f of a plus h is f of 3 plus h. Yeah, the x value where you're trying to find the tangent is always a. All right. Let's see, I don't want to hammer you too hard. I do want to talk about some physics examples, but I'm not crazy about this particular one. So let me see if I can find a better one. Right, yeah, here's our last example. So a ball is thrown up into the air. This classic. Its height, t seconds later, is given by f of t equals 40t minus 16t squared. Find its velocity after 2 seconds. So is the situation clear? I got a dude standing on the ground. At time t equals 0, he throws a ball into the air. The height of the ball t seconds later is given by this. So if I wanted to know the height of the ball after 1 second, I would plug in t equals 1. But I don't want the height, I want the velocity. Remember, velocity, it's basically the same as speed. The difference between speed and velocity is that velocity carries a sign. It's positive if you're going up, it's negative if you're going down. So this is a rate of change. Or a speed, essentially a speed. Since this function is measuring the height of the ball, then what we're really looking for is the rate of change of this function. How fast, how is the height changing over time? I want the velocity at 2 seconds. So what I'm really looking for here is f primed of 2. Because we want the velocity when t equals 2. That means we want the rate of change, the instantaneous rate of change. How fast is the height of the ball changing at that exact moment when t is equal to 2, which is the instantaneous rate of change or speed when t equals 2, which is f primed of 2. So I can recommend strongly something that goes along really well with Calc 1 is Physics 1. And if you Google MIT Physics 1 lectures, the first few lectures for that class, which are available online for free through my MIT OpenCourseware, pair really well with these concepts. So if you want to dive a little bit deeper into the connections to physics, take a look at MIT OpenCourseware Physics 1. They call it 801 there. But if you just search MIT Physics 1 Lecture 1, you'll find it. And you'll see some things that tie these together. And I'll talk a little bit more about them on Wednesday. But since we're short for time here, I'm going to go ahead and get this computation. F primed.
Hey, Professor, can you put the paper up a little bit? Just a little bit.
Up.
Thank you.
So f primed of 2, I'm going to take my definition of the derivative and plug in 2 for a. That's the limit as h goes to 0 of f of 2 plus h minus f of 2 all divided by h. And so Angelic was asking about situations where I would use this formula besides finding a tangent line. This is an example of such a situation. F of 2 plus h and f of 2, I will figure out, and then we'll try to take this limit. So maybe I'll come off to the side here for a second. F of 2 is what I get when I plug in 2 for t. That's 40 times 2 minus 16 times 2 squared. That's 80 minus 64. What is that? Well, that would be 20, so it's 16. And f of 2 plus h is 40 times 2 plus h minus 16 times 2 plus h squared. And there's not much I can do with that, so I'll leave it as it is for now. I'll have to simplify over here. Maybe we'll distribute what we can and clean it up a bit. So that's 80 plus 40h minus 16 times 2 plus h all squared is 4 plus 2 times this is 4h plus h squared. All right, so I'll use that. There is maybe one more thing I could combine here, so yeah, we'll do that. So that's 80 plus 40h minus 16 times 4 is 64 minus 64h minus 16h squared. So what are my like terms there? I've got 80 minus 64 again, that's 16. 40h and minus 64h, that's minus 24h. And then minus 16h squared. So these are the two things that I need to plug in here and here in this formula for my derivative. So I get lim h to 0. F of 2 plus h is all of this. So that's 16 minus 24h minus 16h squared. From that, I'm going to subtract f of 2, which is 16. So I'll put these in parentheses again so we can see where everything is coming from. And it's all being divided by h. Questions so far? Now this limit isn't so bad because we already did all this simplification on the side. This is the limit as h goes to 0. 16 minus 16, those go away, of minus 24h minus 16h squared all over h. And you can factor an h out from the top there. So when I factor an h from the numerator, I get limit h to 0. Upstairs here I'll have h times negative 24 minus 16h all over h like this. So I just factored an h out from the top. And now that I've factored that, I can cancel it with the h downstairs. And I get the limit as h goes to 0 of negative 24 minus 16h. And as I send h to 0, this term goes to 0. That's negative 24 minus 16 times 0, which is just negative 24. Now in these sort of physics problems, the units matter quite a bit. If this is giving the height of the ball in feet and t is measuring time in seconds, then this is negative 24 feet per second. In other words, the ball is falling at this speed, 24 feet per second, 2 seconds after it's been thrown. Now that is right at the time boundary for today's class. So that's the last example I'm going to do. But before we leave, I'd like to answer any questions you guys have. So what feels weird here? What would we like to talk about more? What's on your minds?
I'm just a little confused. How could we have a negative speed? Or, I'm sorry, what?
So remember, the difference between velocity and speed is that velocity has a direction. So if you're falling, then your velocity is negative. If you're going up, your velocity is positive. So when we ask, how is the height changing? I would conclude that at this moment in time, the ball is falling because the sign of the velocity is negative at 24 feet per second. If this was positive, I would say the ball is going up.
That makes a lot of sense. Thank you so much.
Yeah, so it's just direction. Velocity has direction, speed does not.
Thank you.
Of course. Yeah, what else are we thinking? I think we're still a little ways out from the first test. So there was a question about the study guide. I would like to finish up through section 3.3 before giving out the study guide. So we're about a week behind the syllabus because of that holiday. We extended the week 2 material. So right now we're really just starting the week 3 material. At the end of next week, I will send out the study guide. And then the exam will be at the end of the following week. So once we start getting close to the test, I will definitely talk to you guys about it. I'll post announcements on Canvas, and that's also when I'll release the study guide. The study guide is just going to be a collection of problems similar to the homework, but you have to write out your solutions and share those solutions with me so we can talk about them a little bit before the test. But we will talk about that a lot as it gets closer. But we're not quite ready to start on the study guide yet. There will be a new homework that opens up today. It'll open up a little bit later. I have another class to teach right after this one. But then I will publish your homework for this week. And then probably at the end of, what do I say? Where are we now? We're there. Yeah, at the end of next week, I will send out the study guide. Any other questions here?
No, sir.
Everybody else feeling pretty good? All right, then I'm going to go ahead and end our meeting for today. Make sure you keep an eye on that homework. Hopefully everybody who had issues with WebAssign has been taken care of. I got a reply from Cengage regarding one person's trial period extension, but I think there were a few others. I don't know if you guys have been able to get back in or not, but I did email them about everybody who contacted me saying they've been kicked out. If you are still kicked out and you haven't heard back from me or Cengage regarding that, go ahead and send me another Canvas message, and that's how I'll know who still needs attention, and then I will forward that along to the Cengage people. Oh, I see. And some folks are asking about extension requests on WebAssign. I will go in and clear those in just a little bit here also, as soon as I finish with my next class. Okay, that's fine. Yeah, I'm not too stressed about it. If you have an extension request in WebAssign, I'll answer it as soon as I can, probably within the next couple hours. If you haven't been able to finish the homework, but you haven't submitted an extension request, please do so now. That way I will know that you need it, and I will grant it this afternoon. Anything else? Alrighty, so I'm going to go ahead and sign out. I hope you guys, have a great day. Keep working, work hard, and if you do run into any questions, do not hesitate to ask for help. You can Canvas message me, you can email me, and you can come by office hours. I have an office hour today from 1 to 2.